All right, here's a quick little video on using Demoivre's theorem again, and this is really similar to an earlier video that I have created with my good partner, Mrs. Stevenson. But all we did this time was we changed one of the digits to be from +1 plus I to -1 plus I, and we'll see what this does as we try and use Demoivre's theorem to expand out this number. So the first thing we need to do is figure out exactly where we're located on our XY axis, and remember, when you're working with imaginary numbers, the real axis goes left and right like the x-axis does. The imaginary axis goes up and down. Goes up and down like the y-axis does. So if I'm looking at the point -1i, then I go -1 in the real direction, and I go +1 in the I direction. And I'm looking at this guy right here. So here's my angle theta that I'm going to be interested in. And this will be the angle that I work with for this particular problem. So some of the things that I need to know the distance from the origin to my point. And by creating a right triangle right here, I can do that. Remember, I have a 1 unit length here and a 1 unit length here. So when I use Pythagorean's theorem, that's going to be 1 squared plus 1 squared equals the square root of 2. So that's my hypotenuse, is going to be the square root of 2, which when you're dealing with imaginary numbers, that's also the part that looks like it's in the absolute value symbol. Okay, so that's your distance, your magnitude. And so with Demoivre's theorem, I'm going to take that I'm going to take that square root of 2 and raise it to the 5th power. The other thing I need to know is what that angle of theta is that gets me over there. And since I have two sides of a right triangle that are equal, then that tells me that I have a 45-degree angle inside my triangle, which would make this theta then equal to 3 pi over 4. Okay, that's this angle that we're going to sweep out right here is 3 pi over 4. And so to finish my problem off, what I would do is I would look at the cosine of 3 pi over 4 times the power that I'm interested in, which in this case is 5, plus I sine 3 pi over 4 times 5. So this is my setup. This is all the hard work is done now. All we need to do is clean up the math. So the square root of 2 to the 5th power is going to give me 4 root 2. And then inside I have cosine 15 pi over 4 plus I sine 15 pi over 4. Now the problem is I don't know where 15 pi over 4 is located on my unit circle. It's one of my, it says it's a pi over 4 issue, so that's good. I just don't have committed to memory where 15 pi over 4 is. So what I'm going to do is I'm going to, it's obviously bigger than 2 pi. So I'm going to take 15 pi over 4. I'm going to subtract 2 pi from that. And 2 pi over 1 is the same thing as 8 pi over 4. Let's see, right? So, yep. So then what I'm going to do here is I'm going to do 15 pi minus 8 pi, which is 7 pi over 4. Okay? And now this then is the coterminal angle to 15 pi over 4. So to wrap my problem up, I have 4 square roots of 2 times the cosine of 7 pi over 4 plus I sine 7 pi over 4. And when you simplify your 7 pi over 4, you're dealing with now 4th quadrant area. So that's going to be 4 square roots of 2 times positive square root of 2 over 2 minus I square roots of 2 over 2, because you're in that 4th quadrant down here, so your y's are negative, x's are positive. When I distribute my 4 square roots of 2 across, then I'm going to wind up with 4 times 2 over 2 minus 4 times 2 over 2i, which is equal to 4 minus 4i. So there you go. There's another example using Demoivre's theorem, this time with that leading real part being negative.